Video title: Python Qiskit Programming for Quantum Computing, Algorithms and Coding. Greetings from Australia. For more information, comments and collaborations, please contact Professor Dr. Sardar Mn Islam or Naz at Victoria University, Melbourne, Australia. Email address: sardar.islam@vu.edu.au. One introduction. Over the past century, society has witnessed a significant transformation in technological advancements, predominantly propelled by the evolution of computing technologies. These technologies have not only catalyzed scientific innovation but have also significantly contributed to economic growth worldwide. The journey of computing technology began with the massive early 20th century machines and has progressed to today's sleek, highly efficient computers. Traditional computing devices operate within inherent limitations when tasked with complex computations. These conventional systems process data sequentially, bit by bit, using binary bits that exist in one of two possible states, either 0 or 1. This method proves inefficient for handling intricate computations required in tasks such as extensive factorization and molecular simulations, where the computational demands are substantial. In contrast, quantum computing introduces an entirely new dimension to data processing. Utilizing qubits, which can exist simultaneously in multiple states due to their subatomic nature, quantum computing vastly enhances processing speeds for particular problems by refining information more efficiently. This multiplicity in states is derived from the fundamental principles of quantum mechanics, where qubits are depicted in Dirac notation, showcasing superpositions with complex coefficients. Each quantum state is assigned a specific probability, ensuring the total probability of the system remains constant, reflecting the inherent uncertainties of quantum mechanics. Quantum computers leverage these unique capabilities to significantly expand computational power, sparking vigorous research and debate in the field. The distinction between quantum and classical computing is crucial in unlocking new computational potentials. Quantum computing harnesses key phenomena of quantum physics, superposition, interference, and entanglement, to perform multiple calculations simultaneously, enhancing processing capabilities for specific tasks. Superposition allows a qubit to exist in various states at once, not just as a binary 0 or 1 but in any combination thereof. This capability enables quantum computers to process multiple possibilities concurrently. Quantum interference, another critical aspect, involves the interaction of probability amplitudes from different quantum states, which can constructively or destructively influence the computation outcome, favoring the correct responses and eliminating errors. Meanwhile, entanglement, a phenomenon where multiple qubits become interconnected regardless of distance, creates highly correlated quantum states, further boosting the processing power of quantum computers compared to their classical counterparts. Despite these advancements, quantum computing continues to face challenges, particularly in the realm of practical application. To harness the full potential of quantum computing, it is vital to develop and maintain quantum devices capable of executing complex algorithms intended to address real-world problems. This includes automating programming tasks like gate generation and circuit layout to enhance efficiency. Quantum applications necessitate a synergistic integration of classical and quantum processing, heavily reliant on advanced compilation techniques and the development of quantum-specific programming languages. This video aims to explore the foundational concepts and emerging trends in quantum programming languages, offering an in-depth analysis of their structures, functionalities, and supporting resources. Prior to delving into these aspects, it is essential to understand the underlying quantum algorithms that drive these developments. Quantum phenomena exhibit dual characteristics, acting as particles and as waves when not observed. This dual nature facilitates unique events in quantum physics, where a quantum object's state is defined by its wave function, which maintains coherence despite environmental interference. Quantum measurement, the observation process of these objects, can gather data while potentially disrupting the quantum state, leading to possible information loss. At the core of quantum mechanics, Schrödinger's equation dictates how a quantum system's wave function evolves within its energy environment, represented by the Hamiltonian. It is crucial to isolate a quantum system from external influences and minimize energy exchanges to reduce decoherence and maintain system integrity. These principles govern the behavior of quantum objects and are fundamental to quantum computing. Quantum computers utilize three primary features of quantum mechanics to operate at speeds unattainable by classical systems. These include superposition. Superposition is a principle that allows quantum systems to exist in multiple states simultaneously. In quantum computing, this is realized through qubits, which, unlike classical bits that are distinctly either 0 or 1, can embody both states at once, as shown on the screen. Here, alpha and beta are complex numbers indicating the probabilities of the qubit being measured in either state. This characteristic allows quantum computers to process information in parallel, drastically speeding up solutions for specific problems and forming the basis of quantum parallelism. Entanglement. Entanglement in quantum physics signifies a state where multiple qubits are interlinked such that their combined state cannot be simply described by their individual states. Instead, a composite state vector, as shown on the screen, represents all possible combinations of these qubit states. This entangled state enables quantum computers to perform certain computations more swiftly than classical computers, enhancing algorithms like Grover's for search and Shor's for factorization. Interference. The wave-like nature of quantum objects leads to interference, a crucial quantum computing mechanism. When quantum states converge, their probability amplitudes interact, causing constructive, reinforcing, or destructive, canceling, interference. This phenomenon is essential for quantum algorithms, where the manipulation of these interferences can significantly enhance the probability of reaching the correct computational outcome, thereby improving overall algorithmic performance. These foundational principles delineate the remarkable capabilities and the advanced operational paradigm of quantum computing, setting the stage for further exploration into quantum programming and algorithm development. 2 quantum gates in classical computing. Logical gates such as AND, OR, and NOT are integral to the construction of circuits that perform binary computations. These gates manipulate binary inputs either 0 or 1 to produce outputs based on specific logic functions. For instance, a NOT gate inverts its input, transforming a 0 to a 1 and vice versa. In the realm of quantum computing, analogous mechanisms known as quantum gates or qubit gates are employed to manage the states of qubits, which may exist in states of superposition or entanglement. Pauli X-gate. Quantum gates operate as unitary matrices affecting qubit states through matrix multiplication. A notable example is the Pauli X-gate, which functions similarly to the classical NOT gate, effectively altering the state of qubits. Represented by the matrix, shown on the screen, the Pauli X-gate transforms the qubit state, shown on the screen, upon application, as demonstrated by the matrix operation. As shown on the screen, this transformation showcases the basic yet powerful capability of the Pauli X-gate to flip qubit states. Other essential quantum gates like the Pauli Y, Pauli Z, Hadamard, and controlled NOT gates also utilize unique unitary matrices to enable complex quantum computations through their combinations in quantum circuits. Pauli Y gate. The Pauli Y gate serves to rotate the qubit state vector around the y-axis of the block sphere, effectuating both a bit flip and a phase shift. The gate is defined by the matrix, as shown on the screen. This transformation reveals the Pauli Y gate's ability to implement a 180-degree rotation around the y-axis, making it crucial for quantum operations that require both bit flips and phase changes. Pauli Z gate. The Pauli Z gate, often used for phase flip operations, changes the phase of the this gate facilitates the Hadamard gate. The Hadamard gate is instrumental in generating superposition states, allowing a qubit to exist in multiple states simultaneously. It is mathematically represented as shown on the screen. The Hadamard gate facilitates the positioning of a qubit state vector at a point equidistant between the elements shown on the screen, states on the block sphere, crucial for initiating many quantum algorithms such as quantum Fourier transform. Controlled NOT gate. The controlled NOT gate, a 2-qubit operation, changes the state of the target qubit based on the state of the control qubit. The operation is characterized by the matrix, as shown on the screen. This gate is pivotal in creating qubit entanglement and executing conditional operations, essential for quantum error correction and teleportation protocols. By manipulating the entanglement properties, the CNOT gate enhances the capability of quantum circuits to perform sophisticated logical operations necessary for advanced quantum computing tasks. 3 quantum circuits. Quantum computing employs a distinctive infrastructure composed of quantum gates and wires within quantum circuits, similar to how classical computing uses various components to perform specific tasks. Quantum circuits are designed with a specific type and number of gates, orchestrating a unitary transformation that governs the behavior of qubits. These circuits utilize a combination of wires to transmit quantum information and gates to alter qubit states, analogous to how classical circuits operate with traditional algorithms. The intricate arrangement of gates and wires in a quantum circuit determines its functionality, with the outputs of one circuit segment serving as inputs for another. This modular approach simplifies the execution of large quantum algorithms by dividing them into more manageable components. The development and refinement of quantum circuits involve optimizing the number and type of gates and qubits to tackle complex problems effectively. Programming languages like Python, along with libraries such as Qiskit or Cirq, are indispensable tools in the creation and manipulation of quantum circuits, providing the necessary functionality to implement quantum algorithms. Creating quantum circuits with Python. To begin working with quantum circuits in Python, libraries like Qiskit or Cirq must first be imported. These libraries offer comprehensive tools for creating, simulating, and analyzing quantum circuits. Below is an example of setting up a quantum circuit using Qiskit. As shown on the screen, this script imports the necessary modules, creates a quantum circuit with 2 qubits, applies a Hadamard gate to the first qubit and a CNOT gate to both, measures the qubits, and finally simulates the circuit using a quantum simulator. The measurement outcomes are then printed, showing the different possible states of the qubits. Optimizing quantum circuits. For performance, optimizing quantum circuits involves reducing the number of gates and improving the efficiency of qubit usage to enhance performance. Techniques such as gate fusion, qubit reordering, and error mitigation strategies are often employed to achieve optimal quantum circuit performance. Quantum error correction. Quantum error correction is crucial in maintaining the integrity of quantum information and correcting errors due to decoherence and quantum noise. Various error-correcting codes, like the surface code or Shor code, are used to protect quantum information during computation. Quantum circuit visualization. Visualizing quantum circuits helps in understanding their structure and operation. Qiskit provides tools for visualizing quantum circuits, which can be invaluable for debugging and education purposes. Here's how you can visualize a quantum circuit in Qiskit. As shown on the screen, this code snippet imports the visualization functionality from Qiskit and uses it to generate a graphical representation of the quantum circuit. The output parameter, MPL, specifies that the output should be a matplotlib figure, providing a clear and detailed visualization of the quantum circuit. Programming. Quantum computing introduces an advanced paradigm distinctly different from classical computing. Utilizing qubits that can concurrently represent both 0 and 1, quantum computers can process multiple possibilities simultaneously. This capability is harnessed by quantum algorithms, such as Grover's and Shor's algorithms, which leverage quantum parallelism to address problems with previously unattainable efficiency. Grover's algorithm, for instance, enhances the speed of searching through an unsorted database, while Shor's algorithm offers a superior approach to integer factorization, a cornerstone of modern cryptography. Grover's algorithm revolutionizes unstructured search problems by utilizing a sequence of quantum mechanics principles outlined in the following phases. Quantum states in a quantum computer are represented as vectors in a Hilbert space, allowing a superposition of all possible states, as shown on the screen. The Hadamard gate, H, is fundamental in generating a superposition of states. Applied to a single qubit into the oracle in Grover's algorithm marks the correct solutions by inverting their phase, as shown on the screen. This process amplifies the probability amplitude of the desired state through a sequence of operations that include inversion about the mean and application of the Grover diffusion operator, effectively enhancing the likelihood of measuring the correct state. The algorithm iterates the oracle and amplitude amplification steps multiple times to incrementally enhance the solution's probability amplitude. The quantum state is measured upon completion, significantly increasing the probability of identifying the correct solution. Implementing Grover's algorithm in Python. Using Python and the Qiskit library, Grover's algorithm can be implemented to demonstrate its application in solving search problems. Below is an outline for setting up and executing Grover's algorithm using Qiskit, as shown on the screen. Shor's algorithm fundamentally changes the approach to integer factorization, crucial for cryptography. It uses qubits to represent a superposition of all potential factors and employs the quantum Fourier transform, QFT, to find the periodicity of functions, leading to factorization. Implementing Shor's algorithm in Python. Implementing Shor's algorithm requires a deep understanding of both quantum mechanics and classical preprocessing techniques. Below is a simple example using Qiskit to demonstrate the factorization of an integer, as shown on the screen. This example highlights the implementation of Shor's algorithm in Python, utilizing Qiskit to factorize an integer, demonstrating quantum computing's potential in redefining fields such as cryptography and optimization. 5. Quantum programming. Quantum programming has emerged as a critical field for exploring the potential of quantum computing, with various programming languages and frameworks playing pivotal roles. While languages like Python, C, C++, and Java offer simulators and developed environments, Python has become a favorite in the quantum computing research community due to its flexibility and rich features that facilitate problem-solving without the constraints typical of more rigid languages. Python's appeal in quantum programming is also bolstered by features such as dynamic typing, which eliminates the need for explicit variable-type declarations and its interpreted nature, removing the need for pre-compilation. This accessibility enables researchers to easily design, test, and iterate on quantum devices and algorithms. The extensive library and framework ecosystem within Python supports the development of quantum computing applications, making it a leading choice for researchers globally. Quantum programming languages, QPLs, can be classified into functional and imperative categories. Functional QPLs like Qiskit, as shown on the screen, on defining expressions and utilizing mathematical functions for data processing. In contrast, imperative QPLs such as Circ, Scaffold, and Project Q provide a sequence of commands that guide computing operations. This section prioritizes Python-based quantum programming languages and frameworks that integrate well with Python for quantum computing development. Python Installation Guide. Anaconda is a comprehensive software package designed for data science, merging Python with numerous scientific libraries to create a powerful tool for data analysis, machine learning, and scientific computing. It includes Jupyter, a web-based interactive platform that supports code execution, text writing, and data visualization within notebooks. Anaconda distribution is freely available for download at the and provides an easy graphical installer for Windows, Linux, and Mac. For users who prefer not to install software locally, Google Colab offers a web-based environment that supports Python code execution within Jupyter notebooks. It is cloud-based, managed by Google, and available for free at. For those requiring more computational power, a paid upgrade is available. Anaconda and Google Colab do not come pre-equipped with quantum computing libraries, but these can be installed using pip, Python's package manager. For example, to install a library in a Jupyter notebook, use, as shown on the screen, Quantum Computing Toolkit. OpenQASM is an intermediate language for quantum programs designed for direct interaction with quantum processors. It simplifies the construction of quantum algorithms through a set of standardized quantum gates. Qiskit, a Python-based framework, supports the development and simulation of OpenQASM programs. It comprises several components, provides fundamental data structures for quantum computing, offers simulation backends and noise modeling tools, delivers specialized quantum algorithms for various domains, assists in understanding and mitigating quantum program noise. Qiskit also provides access to cloud services, allowing users to run quantum programs on actual quantum hardware from providers like IBM, Alpine, and Honeywell. Its comprehensive simulation capabilities support a variety of computational models, including state vector, density matrix, and tensor network state vector simulations. Let's explore a sample Qiskit program that initializes a quantum circuit with 3 qubits, applies Hadamard gates to each, and measures the state vector length, demonstrating the exponential growth of the state space with the number of qubits, as shown on the screen. This code initializes a circuit, applies Hadamard gates to create superposition states, and calculates the length of the resulting state vector, illustrating the capability of quantum computing to handle complex simulations that classical computers would struggle with. 6. Quantum simulators and quantum computers. Quantum simulators are essential tools that mimic the operation of quantum circuits on classical computers, allowing developers to experiment with quantum algorithms without needing access to expensive quantum hardware. Python offers several libraries for this purpose, such as Qiskit, Circ, and Qtip, which are invaluable for designing, simulating, and testing quantum circuits. Simulating quantum circuits in Python typically involves creating a quantum circuit, adding gates, measuring qubits, and running the simulation to observe results. Here's how you can simulate a basic quantum circuit using Qiskit, as shown on the screen. To execute quantum algorithms on actual quantum hardware, developers must authenticate their Python code with the quantum provider's API, select a quantum device, adjust the circuit to the device's specifications, run the circuit, and analyze the results. This process allows researchers and developers to test their quantum algorithms in real-world conditions, providing invaluable insights into their effectiveness and potential applications. With Qiskit Quantum Machine Learning, QML, represents a fascinating convergence of quantum computing and machine learning, where quantum algorithms are applied to enhance the efficiency and capabilities of learning algorithms. The Qiskit framework, developed by IBM, plays a significant role in this emerging field by providing tools and libraries specifically designed for quantum computing applications, including machine learning. Quantum algorithms for machine learning. Several quantum algorithms have been adapted or developed specifically for machine learning tasks. These include the Quantum Support Vector Machine, QSVM, Quantum Principal Component Analysis, QPCA, and Variational Quantum Classifier, VQC. Each of these algorithms leverages quantum mechanics to process information in ways that are fundamentally different from classical approaches, potentially leading to faster processing and reduced computational resources for certain tasks. The QSVM utilizes the quantum-enhanced feature space to perform classification tasks more efficiently than classical SVMs, particularly in handling large datasets with complex patterns. The mathematical basis of QSVM involves mapping input data into a high-dimensional Hilbert space using a quantum feature map, which is non-linear and can capture complex patterns in the data. As shown on the screen, represents the parameters of the quantum circuit used as a feature map, transforming the classical input data as shown on the screen. As shown on the screen, QPCA is designed to reduce the dimensionality of quantum data. It uses quantum phase estimation to estimate the eigenvalues of the density matrix that represents the data, which corresponds to performing PCA in the quantum state space. As shown on the screen, VQC uses a hybrid quantum classical approach where a variational quantum circuit is employed to perform the classification. The parameters of the quantum circuit are optimized using classical optimization techniques to minimize a cost function defined by the classification error. As shown on the screen, the integration of quantum algorithms into machine learning through Qiskit provides a powerful toolkit for researchers and developers looking to explore this cutting-edge domain. By utilizing quantum properties such as superposition and entanglement, quantum machine learning can potentially solve complex problems more efficiently than classical methods. As the field of quantum computing matures, the development and refinement of these quantum machine learning algorithms in frameworks like Qiskit will play a crucial role in realizing their full potential. Conclusion: quantum computing holds immense promise. Essential to this advancement is collaboration across various fields and institutions, fostering breakthroughs that could be emulated and possibly surpass the historical progress of classical computing. Researchers are leveraging decades of computational evolution to inform the development of quantum technologies. A pivotal element in this journey is the evolution of quantum programming languages. These languages are critical for representing quantum algorithms and delving into concepts such as qubits, gates, superposition, and entanglement. They facilitate the exploration of quantum theories and support the development of practical applications and the underlying hardware. This necessitates a holistic approach involving hardware, firmware, control software, compilers, and programming languages working in concert. Currently, quantum compilers lag behind their classical counterparts, primarily focusing on optimizing low-level circuits rather than entire programs. The next step in compiler evolution is logical compilation strategies that transcend specialized task solutions, aiming for more generalized and effective outcomes. Quantum programming languages are evolving to incorporate quantum-specific keywords and constructs that enhance computational efficiency. As quantum computing continues to mature, we anticipate that quantum languages will adeptly manage algorithms of increasing size and complexity, thereby elevating design model intricacies. Quantum programming is poised for dynamic growth, with future research directed towards enhancing quantum compilers. This entails developing innovative compilation techniques specifically tailored to the unique requirements of quantum computing, including quantum-specific optimizations and refined protocols for operating quantum devices. Looking ahead, the development of new quantum programming paradigms and languages will be crucial. These innovations will better articulate quantum concepts, particularly the abstractions required for handling groups of qubits of various sizes. As quantum technology scales, programming individual qubits becomes increasingly impractical, thus necessitating these advances. Additionally, research efforts will focus on providing tools and frameworks that facilitate collaboration, communication, and knowledge sharing within the quantum computing community. This will include the creation of reusable code libraries and educational resources to aid those new to the field, thereby nurturing a robust ecosystem for quantum computing development.